Okay, let's talk about something we use literally every second of every day, but almost never think about: electricity. Today, we're going to go on this incredible, kind of invisible journey that it takes just to get from the power plant all the way to your plug.
You know, have you ever really wondered what happens when you flip a light switch? It feels instant, right? But that simple little flick, it's actually the very last step in a truly colossal journey. We're talking a trip that can start hundreds of miles away and involve some pretty mind-boggling changes in power.
Yeah, when you flip that switch, you're not just turning on a light. You are literally completing an electrical circuit that stretches back for miles and miles, sometimes even thousands of miles, all the way to a power plant. It's this amazing journey of immense power, super precise engineering, and, as we'll see, constant transformation. So to really get our heads around this, we're actually going to trace this journey backwards. Yeah, we'll start right there at the familiar plug in your wall and travel all the way back to where the electricity is made. And we'll see how the power changes at every single step.
All right, so here's our starting point: 230 volts. That's the standard, relatively safe voltage that comes into your home. It's just the right amount to power your laptop, your lights, your whole life, really. Think of it as a manageable amounts of electrical pressure.
And this little map here, it basically shows the entire journey. You've got power being generated way up at the top, then it's transmitted over these huge distances, and finally, it's distributed down to us, the consumers. The key thing to notice, the really important part, is how that voltage gets stepped down at each stage. So let's take our first step backwards from our house and see what that looks like.
Okay, step one. Just outside your neighborhood, you've got the local distribution lines, and these things are carrying electricity at around 11,000 volts. Whoa, right? That's way, way too high for your house. And that's exactly why we have transformers. You've seen them, those green boxes on the ground or the gray cans up on the power poles. Their whole job is to step down that voltage before it gets to your front door.
All right, let's take another step back. Now we're at the sub-transmission network. Here, power is zipping between whole regions at something like 132,000 volts. You're starting to see the pattern, right? The further away we get from your home, the higher the voltage gets. And this is not random at all. It's actually the secret sauce to making the whole grid work efficiently. And then we get to these guys. This is the absolute backbone of the entire system. These massive towers are holding up the primary transmission lines. Think of them as the superhighways for electricity, just moving enormous amounts of power over huge, huge distances. So what's the voltage on these superhighways? Get this, it can be as high as 765,000 volts. Let that sink in. That's more than 3,000 times the voltage coming out of your wall. Now, why so high? Well, this super high voltage is absolutely crucial. It's how they minimize the amount of energy that gets lost as heat when the electricity travels for hundreds of miles. And less energy lost, that means a more efficient grid and, hey, lower electricity bills for all of us. Okay, so we've traced the whole journey, but what are the actual rules that make this all work? What's governing this incredible flow of energy? Well, it all pretty much boils down to one golden rule. First up is voltage. We've been throwing that word around a lot. The easiest way to think about it is just as electrical pressure. Seriously, it's like water pressure in a pipe. That pressure is what pushes the water through, and voltage is the force that pushes all those little electrons through a wire. Then you've got current. So if voltage is the pressure, then current is the actual flow. It's how much electricity is actually moving through that wire every second. Sticking with our water analogy, it's like asking, how many gallons of water are flowing past me right now? That's the current. And finally, piece number 3, resistance. See, every material out there resists the flow of electricity at least a little bit. It's basically friction in the system. A really narrow pipe is going to have more resistance to water flow, right? Same idea. A thin wire has more resistance to an electrical current. So how do these 3 things, voltage, current, and resistance, all fit together? Well, it's all captured in this one beautifully simple formula called Ohm's law. It just says that voltage, the pressure, is equal to the current, the flow, times the resistance, the friction. That's it. That is the golden rule that runs almost every single electric circuit on the planet. Okay, so applying that golden rule to just one wire is pretty straightforward. But the power grid, that's a massive, crazy interconnected network of wires. So to manage all that complexity, engineers came up with a special kind of language, a way to classify and analyze all these different networks.
So first up, engineers make a distinction between linear and nonlinear networks. A linear network is nice and predictable. Its resistance doesn't change, and it follows Ohm's law to a T. This is absolutely vital for the main grid, where you need stability above all else. Nonlinear networks, on the other hand, are more complex. Their properties can actually change, which makes them a lot harder to predict.
Next up, we have bilateral versus unilateral. In a bilateral network, which is what most of the grid's wires are, the current can flow in either direction. Easy enough. But in a unilateral network, it's a one-way street. And this is super critical when you get to modern electronics and all the control systems that we plug into the grid. They use things like diodes to make sure power only flows in one very specific direction. So if engineers have this language to describe all the different networks, how do they actually sit down and analyze them? I mean, a real-world circuit diagram can look like an impossibly tangled mess of spaghetti. The secret is to simplify it, piece by piece. Just take a look at this thing. At first glance, it looks crazy complicated, doesn't it? You've got multiple paths, all these different components. But believe it or not, we can use those basic rules we just learned to boil this whole mess down into something, well, something incredibly simple. And the way they do it is actually pretty logical. Engineers just systematically combine all the different parts. You can see it in the diagram. First, they find components that are in parallel with each other and figure out a single value for them. Then, they find components that are in series, one after another, and they just add those up. And they just repeat that process over and over. Combine the parallel parts, combine the series parts, until that big, complex web turns into one simple circuit. It's a really powerful way to make sense of all the chaos. All right, so we've traveled from your wall outlet all the way back to a power plant. We've learned the golden rule of electricity, Ohm's law, and we've seen how engineers take all this complexity and make it manageable. But so what? Why does any of this really matter? Well, it matters because this invisible system is what our entire modern world is built on. The really key things to take away are these. First, electricity's journey is this long series of transformations. Second, high voltage is for efficiency over long distances, and low voltage is for safety in our homes. Third, all of it is governed by the beautifully simple Ohm's law. And finally, engineers use this methodical simplification to design and manage the whole incredible thing. And this quote here really just nails it. The whole massive power grid only works because of the simple rules that govern its tiniest little parts. You know, the grand design is only possible because the tiny details are so perfectly understood. And that kind of leaves us with one final thought. This system we have, it's a monumental achievement, and it powers our world today. But our needs are changing, right? So the big question becomes, using these exact same fundamental principles, how do we engineer the smarter, more efficient, and more resilient grid that's going to power our future?